Hey geometry students, I am going to go ahead and talk to you about 2.1 lesson, and we are on page 35 of your student journals. All right, we're going to start with these first four vocab terms, and we're just going to lump these together into kind of like one little, definition of sorts. And so what a conditional statement is, it's a logical statement. And so that's one of the things I want you to know. It's a logical statement that has kind of two parts. So it'll go something like this. If something happens, then this happens. So what we may call this is like an if-then statement. Like, if it's sunny out today, then I will go for a walk. That's called a logical statement or a conditional statement. So a conditional statement has to have two parts. And so that first part is called our hypothesis. And so that's kind of this part. And the conclusion would be the last part. So the if part is your hypothesis, and the conclusion would be your then part of your statement. We call this the if-then form. So like when we write this, we call it an if-then form, like if this happens, then that occurs. And so this is kind of all kind of lumped together, and these are all kind of related. What it means by negation is the opposite of the statement. So like if I did the if-then statement of, if today is Monday, then I go to school. And then the negation would be, if today is not Monday, then I don't go to school, that kind of thing. A converse, so a negation, it would be something like, we would call this not P. So let me make sure I've talked about this. So we call this like the hypothesis, the P part of your equation. And we call the conclusion the Q part. So like we'd say, if P, then Q. So the opposite so for a negation, it would just be the opposite of one part of that. So like, for example, if my statement was, if today is Monday, then I go to school, then the opposite or negation, this is the symbol, looks like a little kind of a wave. That means negate P. That means the opposite of whatever you said in part P. So the statement I said in part P was, today is Monday. So this would be today is not Monday, that kind of thing. So it'd be the opposite of whatever we put in part P. The converse is where you exchange your hypothesis and a conclusion. So you kind of put them in the opposite order. So for a negation, for a converse, how we write it is we would say Q implies P. So if our normal statement is P implies Q, because P comes first, then Q, and a negation would just be the opposite of either P or Q, a converse means you just flip the order. So with this, in our example where I said, if today is Monday, then I go to school, my converse would be if I go to school, then today is Monday. And so what you're going to look at here is like, are these statements going to be true or false? Are they always going to be true? Are they always going to be false? Is the converse going to be true or false? That kind of thing. So then we get into inverse. So the inverse is basically where you negate both the hypothesis and the conclusion. So it's kind of a combo. So negate the hypothesis and the conclusion. So what it would look like in symbols for the inverse, it would look like not P implies not Q. All right, so this little symbol, this negation, that little kind of wave thing that I write, I always use it as the word like not, because it's kind of like the opposite, right? So the opposite of P. So this would imply if it's not Monday, then we don't go to school. So instead of it saying, if today is Monday, then I go to school, I would say, if today is not Monday, then I don't go to school. That would be the inverse of my statement. All right, contrapositive. So this is, again, kind of a combination thing. So the contrapositive is you basically do the converse, so where you switch them, and also apply a negation. So you negate the converse All right, so in symbols, it's a little easier to kind of think about this one. This would be not Q implies not P. So again, back to my example of if I go to school, then today is Monday. This would mean if I don't go to school, then today is not Monday. So again, that's what we mean by contrapositive. So it's a little easier to think of it in terms of like letters, I think. Like P implies Q. Negation means not P or not Q. Converse would just be you switch them around. Inverse means you keep them in the right order, but you make them the opposite or not. And then contrapositive is where you flip them and negate them. So you kind of do both. All right, so that's fun, right? Now we're going to talk about some other, hopefully less confusing things. So equivalent statements. So basically equivalent statements are statements that are either both true or both false. So you'll see this, with various, we're going to give you lots of different examples in the book, and of course you're always welcome to do more problems than what I kind of give you for practice. But basically they're just looking at if I said if today is Monday, then I go to school, is that true, or is that false? And so what we're looking at there is for equivalency. This idea of perpendicular lines, you guys already kind of know, but we're going to talk about this again just to be sure. Perpendicular lines are two lines that intersect at a right angle. So this terminology comes up again, which is why I wanted to review it. Two lines that intersect at a right angle. So what's going to be important again is notation. So a lot of times this is kind of the symbol, and we use a little right angle symbol. It's not required to put a right angle symbol in all four of those quadrants, because if this isn't a right angle, then it already dictates that the rest of them are right angles because of the fact of these are linear pair or vertical angles. All right, now we're going to go back to a biconditional statement. So this is kind of going back to what we were talking about here with the P's and the Q's. A biconditional statement is when the conditional statement and its converse are both true. So conditional statement, so that's that if-then statement, the P implies Q, and its converse are both true. So when that occurs, when the conditional statement and the converse are both true, we can kind of reword this and call it a biconditional statement by saying, so let's think of something that would be, something where if it's a biconditional statement would be something like, if two angles are complementary, then their sum of their measures is 90 degrees. So the conditional statement is, if two angles are complementary, then their sum of their angles is 90 degrees. That's true, right? The converse, which would be the opposite way around, would be if two angles have measures of 90 degrees, they add up to 90 degrees, then they would be considered complementary. Okay, that's true as well. So basically what we said here is in that statement, the conditional statement's true and the converse is true. And when that happens, we can rewrite it in what we call an if and only if statement. So we can say, we might say, two angles are complementary if and only if, so that's the main part there in a biconditional, if and only if they add to 90 degrees. So in a biconditional, we kind of take out the traditional if this, then that, and we kind of write it as like kind of a real specific statement, like it's always going to be true. So we use this if and only if. I just want you to know that a lot of times when we abbreviate, a lot of math books will abbreviate this, and I like to abbreviate this. Instead of writing if and only if all the time, I write IFF, which implies if and only if. But again, just to make sure that you understand that. All right, now the last couple things we're going to talk about in this unit are something called truth tables or truth value. So a truth table is basically taking a logical statement, so like the P implies Q, and kind of using a table to kind of determine if the statement or the conditional statement is true or false. So a truth table, I'll just have you write down, determines if the conditional statement, so that's the if-then statement, is true or false. So it's just like a logical way to kind of process kind of that information. A truth value is basically what happens is when you write, I'll show you an example of a truth table, but in a truth value, you have either an option of, well, something can either be true or it can be false. So basically you have two answers. So when you look at like the conditional statement, whatever it may be, P implies Q, the answer to P, like if you ask, okay, is P true or false? So there's only two choices there. And then you look at Q, is true or false? And then you'd only have two answers there. So they call that a truth value. So when we answer that question, or when we try to figure out whether it's true or not, we call that a truth value, a true or a false. Let me show you an example of a truth table. So if you want to grab a piece of paper, because this is not part of your notes, or like for me, I'm just going to turn this paper over because I have some room on the back, so I don't know how, you probably don't because you have it in your book, but maybe grab a sheet of paper. I just kind of wanted to show you a traditional like truth table. So this is a truth table. Well, we're going to do a truth table. So we're going to do P implies Q. And so what a truth table is, well, first it's a table. So I'm going to draw a table. And basically what we have is we have P, we have Q, and then we have P implies Q. So I'll show you what that looks like. So we have a statement P, we have a statement Q, and then we have P implies Q. So I'm not using a specific statement here because we're talking about, this is called a logic statement. In other words, we're not really talking about something specific, we're talking about an entry in here, right? So like any P, any Q. And so what we're looking at, let me draw in some rows here. So this would be a truth table. So the definition on the other page about a truth table, this is an example of a truth table. And so whatever I put in for my answers would be called your truth value. So for example, we could have so the traditional logic statement kind of goes like this. If, we could answer true for P and true for Q, then that means P implies Q would be true. So that would be a true statement. If P is true but Q is false, then that would have to equate then that my conditional statement is false. And then if I have P to be false but Q is true, it's going to result in a true statement. And then false, false, and true. So this is what our standard logic statement is going to look like. So these are kind of like our outcomes. So if we know that P is true and Q is true, it's always going to produce a true outcome. And if we know P is false and Q is false, it's still always produce a true outcome. So what we'll be asking you to do is kind of to manipulate some of these truth tables to kind of show a variety of different scenarios. So for example, I'm going to walk you through one that's a little bit more complicated. So let me show you. Lots of symbols. So what this means is not P implies Q. So again, kind of confusing, right? So what we're going to do is I'm going to show you a truth table. And I'm going to make this one a little bit bigger because we have a little bit more stuff to add in it. And then I'm going to do P and Q. And then I'm going to do one for not P. So like, I know I have P and Q, right? But then I need to have another one for not P because there's a whole thing for not P. And then I want to have another whole column for not P implies Q. And then another whole column for not P implies Q. So if I haven't confused you yet, this is what I mean. So our entries are, we know we have P, we know we have Q. Well, in this particular statement, I have a not P. So I need to include that as one of my entries. The other entry I have is this one right here, which is not P implies Q. And then my last, excuse me, my last entry is the entire statement, which is not P implies Q. So we're kind of looking at like each individual one. All right, so let me draw in my rows here. So again, this first part of your table is actually just the same thing as what we did above. So P implies Q. So we got true and true. We've got true and false, and this will always stay the same. False and true. Move this up a little bit. And then I have false and false. All right, so because I'm not just looking at P and Q, I'm looking at not P. So now I'm going to do the opposite of P. So look at your row for the P's, and you're going to do not P. So basically you're taking the opposite. So if P was true, it's now false. If P is true, it's now false. If P is false, it's not true. If P was false, it's now true. So you just did the opposite of all the values that were in the P. So now you're going to say, okay, let's put those together. Let's put this column, what happens when I have a not P, which is a false, with a Q, which is a true. So what happens when I put a false with a true? We'll go back up to your table. What happens when I do false and true? Well, I get a true outcome. Okay, let's do the next one. What happens when I get a not P with a Q? So a false with a false. False and false ends up with true. Okay, what happens when I get a true with a true? We know that's true. And then a true with a false. So if you look back up at your table, a true, then a false is going to equate to a false. Okay, almost there. So then the last statement, or the last thing, I guess, if you will, is that we're going to kind of do the opposite, or the not, of not P, not Q. So this is all not P, not Q, right? This whole thing. So that's this middle part. So now we're just going to take the opposite, or the not of it. So if this was true, it's now false. If this was true, it's now false. If this was true, it's now false. If this is false, it's now true. So in our statement, if I have not P implies Q, I have 3 scenarios in which it's going to be false, and 1 scenario that it's going to be true. I think in one of the examples, it does ask you to kind of create a truth table. So this is definitely a more complicated one than probably what you're going to see in some of your homework, but I figured I'd go over one that was a little bit more complicated, and then you guys can do ones that are a little bit more straightforward. All right, so just to kind of clarify, I wanted to make sure you guys understood. So we have all of these different conditional statements and so forth. So I'm just going to write down the statement. I'm just going to give you an example in words. So I'm just going to use that one I talked about. If today is Monday, then I go to school. So this is our, today is Monday is our P, and that I go to school would be my conclusion. So hypothesis and conclusion. Okay. Next one, negation. And so this was basically like saying you're just going to do the opposite of one of them. So like if I did not P, like the example says, I would say, you know, today is not Monday. Right? So that would be the opposite, or not, of that one. On the bottom, these are the ones that are converse and inverse. So converse was the one where it was just the opposite order. Okay, so then the statement would look something like, if I go to school, then today is Monday. So that's like the opposite order. The inverse would be not P implies not Q. So this means if I go to school, I'm sorry, oops, let me make sure I get that right. If today is not Monday, so if today is not Monday, then I don't go to school. So that's kind of the inverse version of that. Next page, we're on page 37. So now we're looking at the contrapositive. So the contrapositive has us talking about not Q and not P. So in words, what this would look like is if I don't go to school, then today is not Monday. And then the final one is that biconditional statement, and I already gave you an example of one with the complementary, but in case you didn't write it down, we can write it down here. We can say, you know, 2 angles are, we'll change it to supplementary, how's that? 2 angles are supplementary if and only if, so I use the IFF, if and only if the sum of measures is 90 degrees. Oh, I changed it, right? So 180 degrees. The sum of their measures is 180 degrees. And so that's what we use for like a, that's what we use for a biconditional statement. So that if and only if. That implies, again, that both of those statements are true and the converse is true. So we're talking about both scenarios. All right, this video is getting a little long, so I don't want to do a ton of stuff, but I thought I'd go over a couple examples on the extra practice and then maybe give you guys an opportunity to maybe try to do the rest on your own. So I will go over, so the first one says, rewrite the conditional statement in if-then form. All you're really doing is just putting the if and the then in front of it. So I'll do the first one, like if 13x minus 5 equals negative 18. So this is obviously a very math one. Then x equals negative 1. So that's what they mean by just writing it in if-then form, like literally putting it into if-then form. So I'll have maybe you guys try number 2. Number 3 is kind of a big one. I'd like to see what you guys do with this. So what they're having you do is do all of the examples. Do a contrapositive, do a converse, do an inverse, like do all of them. You're probably going to need a little bit of room, so maybe on a separate sheet of paper you'd write those down. But those would be a good one to try, and then we could talk about that one in class, just because it would kind of goes through all of the definitions. And then lastly, on this bottom part, it's just asking you to talk about like logic statements, basically. Like, do you know these are true? So they're decide whether the statement in the diagram is true, explain your reasoning using any kind of definitions we've learned. So what I want to show you is like LM bisects JK. Do we know that statement is true based off of what we have marked? And the answer is yes, we know it's true. And the reason why, because we said LM bisects JK. So first of all, what's being bisect? So JK is a segment, J to K is a segment. JK is the one being bisected. And if you notice, it has these two little marks on here, which implies that those are congruent, which again means that they are equal. So I'm not going to read it all out, but explain your answer using definitions. We know the definition of bisects means it cuts it in half. And therefore, we know since those two things are marked as congruent, we know that those are indeed being bisected. I'll do the number 5 with you. So this one says JRP and PRL are complementary. So JRP and PRL. So basically these two angles right here, they sure look complementary to me, right? They look like they're 90 degrees. But if we don't know that they're 90 degrees, we cannot say that they're 90 degrees. So I'm going to say false. And what we're missing is that right angle symbol. So if they had the right angle symbol in here, then I would say absolutely, they're going to definitely be complementary. They look complementary, but I don't know that they are. You know, what if this both adds up to 89.9 degrees? Technically, that's not complementary, right? So we got to be careful there that if it's not marked, we're not calling it, truth. All right, kind of a long video. I apologize, but there's lots of stuff in this one. And if you have any questions, write them down, bring them to class, ask. All right, thanks, guys. Bye.